We'd like to draw some conclusion about what we've talked about in primal bounds. The first thing to note is that a primal bound is really anything that's a feasible solution. In a maximization problem, the primal bound is going to be a lower bound on the optimal solution, and really the only way that we can do this is by finding a feasible solution to the integer program. Any technique that we can use to find a feasible solution will do. We'd like to inherently find a good feasible solution, one that's pretty close to the optimal solution. And we've given two particular routes to do this. One are the LP-based techniques, where we take a linear program and round it. The other is more heuristic, where we have a greedy algorithm or a local search technique. Among LP-based techniques, we've done a simple rounding scheme where we take a linear program solution and round it to an integer solution that satisfies our integer programming constraints. And we also saw a more powerful technique of iterative rounding that expends more runtime but could potentially get better solutions, especially when our linear program solution is very homogeneous. What's important about these linear program-based techniques is that they give a corresponding dual bound. If we use a linear program-based technique, like iterative rounding for example, the linear program provides a dual bound, an upper bound. The feasible solution we generate provides a lower bound, a primal bound, and we can measure the gap between them. In this way, when we use a linear program-based technique, we can measure the quality of our solution by comparing it to the original linear program solution, the unrounded solution. In the heuristics we saw the greedy algorithm and the local search algorithm. Both of these algorithms are heuristic in that they have to be tailored to the problem at hand, and the particular things we do in each of these problems are going to be very different. There's some general guidelines to work around though. The problem with greedy algorithms and local search algorithms is that there is no automatic dual bound. There's no linear program we solved, so there's no dual bound to compare our solution to. All we've done is we've generated a feasible solution. In some cases this is okay though, and in general greedy algorithms and local search algorithms run very quickly. The way we should view this is, we've talked about primal bounds and we know that they consist of feasible solutions, and we have some tools for us now that we can generate feasible solutions. In one case, we can actually measure the quality of them, and the other case we can't. We should consider this as just the beginning. As we go through the course, we're going to find a lot of different ways to generate primal bounds or feasible solutions, and most of these techniques are going to give us the corresponding dual bound. They're going to be like the linear programming based techniques. This way we can measure the quality of our solutions. There's going to be a lot more to come on generating primal bounds.